Good morning. Welcome back. Probably felt like you never left for the weekend. But anyway, good to see you this morning. And you saw my message over the weekend about the last quiz. And you're welcome. And the opportunity you have to gain back some points. Were there any questions on sort of the process for that? Hopefully that was clear enough for you in the message. All right, so, okay, yes.
Like why you got wrong? You just got the wrong answer.
Well, you can put why. So what I'm looking for is not why you got it wrong and that explanation, but why the new answer that you put there is right. Okay, so that's what I'm looking for. Yeah, I don't care what happened to get to the wrong answer, but yeah, if you could sort of tell me how you got to the right answer, just a sentence is good. So you can tell me what happened if you want, but you know, if there, with that being said, seriously, if there was something with the way a question was written and you want to sort of just put a note for that could be helpful. But I'm not requiring that. So.
Our class average is 4 point something. I have a feeling that on this part of the exams, we're not going to do so hot. You know, so are we gonna your maybe final your exam gonna be similar to this maybe, so we can something based on, because even though we try to study what in the past, we might recoup whatever. See what I'm saying?
Right. So you will gain the points here. You know, what I'm hoping by doing it this way is that this will be partly a learning process as well, so you can sort of delve back into that material and see where you went wrong and hopefully improve. And so that way there, when it comes to the exam, I don't know what the exam questions are going to be at this point, but that's my idea for this assignment, is that rather than just being like, okay, this is, you know, the worst quiz ever in my life, that you have a chance to sort of review the material. So, any other questions? All right, with that being said, the next time I see you, assuming it's not in the hall but in this classroom, we will start off with another quiz. So the idea here for the number of quizzes is just to keep you up with the material and not let you get too far behind. And so that's why we have our next quiz on Wednesday. And last week you saw the topics for that. And so please review that before Wednesday. So let's continue here, or let's move on to our material for today. And we are continuing with our discussion on protein synthesis. And last class, we started to talk about the ribosome and how that's involved in protein synthesis. And we talked about, you know, the different parts of the ribosome, right? The large ribosomal subunit, the small ribosomal subunit. We've talked about the aminoacyl tRNAs. And so what we're going to do today is we're going to see, first of all, how these different pieces come together to carry out translation. And we're going to start with a discussion of what's happening in prokaryotes. And one of the reasons why this is especially important for us to understand is not, well, okay, sure, we might just like to learn about prokaryotes, but also once we start getting into microbiology next semester and then start talking about some antibiotics, well, a number of these are going to be inhibiting translation in bacteria. In addition, many of the things that we know about translation is actually because of experiments that were done in bacteria as well. So we'll talk about what's happening in bacteria first, and then we'll talk about what happens in the eukaryotes. So one of the questions here for us to start with here is, how is the start site for translation determined? Right, so we know that an AUG is going to be involved. And you might just think that it makes sense for the ribosome to hop on to the 5' end of the mRNA and just keep going until it finds the first AUG. And in prokaryotes, that's not exactly what happens. Okay, in eukaryotes, we'll talk about that in a minute. But in eukaryotes, that is sort of what happens. But for prokaryotes, that's not what happens. And what happens now is that there's actually going to be a specific AUG for each mRNA that gets used. And what happens is there is a specific sequence called the Shine-Dalgarno sequence. And here in blue on the slide are several Shine-Dalgarno sequences. And you don't need to memorize these sequences, but what you should know is that the Shine-Dalgarno sequence gets bound by the small ribosomal subunit. And more specifically, there's a particular ribosomal RNA that's found in the small ribosomal subunit that binds to the Shine-Dalgarno sequence. And this Shine-Dalgarno sequence, notice that it is positioned, a bit upstream of usually an AUG. Occasionally, there is a different start site for that codes for valine. You see this GUG here for one of these. Rarely this is used as the start site, but sometimes it is. And what happens now is by having the small ribosomal subunit bind to the Shine-Dalgarno sequence, that then determines that this nearby AUG is going to be the start site. So for instance, do you think there are going to be other AUGs in the mRNA? Yeah, quite likely. But nonetheless, it's going to be the AUG that is nearby this Shine-Dalgarno sequence. So that's the Shine-Dalgarno sequence. And that's, again, how we identify which start codon or which AUG codon will be used. As for the tRNAs, there are 3 primary sites where tRNA molecules are bound by the ribosome. And I mentioned these to you last class. And these are the A site, the P site, and the E site. You can know them by their letters, but just so you know, the A site stands for aminoacyl. The P site, the P there stands for peptidyl. And then the E site stands for exit. And so now, when we talk about elongation, the tRNAs are going to be moving from the A site to the P site to the E site. So they're going to be going APE. Okay, so remember that. So APE is the movement, is how the tRNAs are going to be moving through the ribosome. All right, so that's what's happening with the tRNAs. So what I'd like to do is, remember last class, I told you the three general processes involved in translation are going to be initiation, elongation, and then termination. So let's take a look at what happens for each of these, and we'll, of course, start with initiation. And so what's happening here to get everything together to start translation? So obviously, we're going to start with probably or at least I should say it this way, the ribosomes will be involved here somehow. And initially, we'll start with the 30S ribosomal subunit. So this is the small ribosomal subunit here. And what happens is this small ribosomal subunit gets bound by a couple of initiation factors, IF1 and IF3. And these do a couple of things. So the IF1 and the IF3 do a couple of things. So they bind to the small ribosomal subunit, and in doing so, they help to prevent the large subunit from prematurely binding. In addition, they also help to prevent some tRNAs from also prematurely binding as well. Okay, and that's a major role here for the IF1 and the IF3. Next, another initiation factor called IF2 is involved. And this IF2 is bound to a couple of things. First of all, it's bound to a molecule of GTP, which you'll see what happens to that in just a second. But in addition to this, it's also bound to a special initiator aminoacyl tRNA. Again, there's the special initiator aminoacyl tRNA. So when we say that most proteins in prokaryotes start with a specialized amino acid, that relates to what we're talking about here. And what is that? So it's methionine, but attached to a formal group. Okay, so in prokaryotes, the first methionine that is added to a protein is not regular, plain old boring methionine, but rather it is methionine with this formal group added to it, which is shown right here on the slide in pink. So for the first methionine here in prokaryotes, it's going to be this modified methionine. And so now this initiation factor 2, bound to GTP, bound to the aminoacyl tRNA that contains this F-methionine, this comes in and along with the mRNA, it now binds to that special tRNA, binds to the AUG that is going to be near the Shine-Delgarno sequence, which is not shown on this slide. And now, this, along with the small ribosome, this all comes in and binds to the mRNA here. And one of the keys here is that this first aminoacyl tRNA binds to the P site of the ribosome. So that's not on your slide here, but that's an important point here, that this first aminoacyl tRNA is binding to the P site of the ribosome. Once we get this first complex formed here, then what happens is sort of all at once here, the IF1 and the IF3 are removed, so they diffuse away. In addition, the IF2 converts its GTP to GDP, which triggers its removal. And now, with these initiation factors out of the way, the large ribosomal subunit can come in and bind. And at this point, again, we have our first aminoacyl tRNA found in the P site of the ribosome. And now initiation is complete, and we're ready to move on to the next step of translation. Are there questions with initiation? Yes?
Every protein does start with a methionine. It's not like the start signal, it's just a signal without actually having an amino acid.
Yeah, so the first start site is indeed going to code for an amino acid. 99 point something percent of the time, it's going to be, in prokaryotes, it's going to be this modified methionine, the formal methionine. Whereas rarely, right, it would be, say, a valine. There are a couple of examples in bacteria where it's actually valine that starts. But by and large, it's going to be methionine, and it's always going to be an amino acid that gets coded here.
So you say, so this is initiation for prokaryotes?
Yes.
Eukaryotes?
Yes. Yeah, so this is for prokaryotes here. One of the differences that we'll see between prokaryotes and eukaryotes is that for eukaryotes, we're going to be using plain old boring methionine for the first amino acid here. But again, with the prokaryotes, it's going to be the formal methionine. Yes?
I have a question. So this formal methionine, is that a unique tRNA for it?
Yes, exactly. So that's a very good question. So indeed, this is going to be a different tRNA that is used than the one that codes for regular methionine later on in elongation, say. So yeah, so this is indeed a different tRNA that is used here. Yes?
You said the IF1 and the IF3 were just to the delay.
Yes.
No enzyme or anything that comes in to do that.
Yeah, well, what happens here is sort of all together, and it might be the IF2. So if you look at a later slide, so this slide here has things in this order. A later slide I'll show you actually reverses the order of what happens with the IF3, IF1 versus IF2. And what really happens, I think, is they're happening at the same time. And it may be that the GTP hydrolysis that is occurring with the IF2 is the factor that is leading to things coming off of the ribosome, this small subunit of the ribosome. Okay. Other questions? Okay, well, let's see what happens with initiation now. And so, elongation now. So again, this is just to orientate you to this slide, right? So we now have our ribosome with that first aminoacyl tRNA that is bound to the P site of the ribosome. Okay, so that's where we left things off on the last slide. So now what happens for initiation is that we have our mRNA where the next codon is going to be found in the A site of the ribosome. And so what happens now is the next aminoacyl tRNA that has an anticodon that binds to the codon of the mRNA in the A site. This aminoacyl tRNA comes in and can bind. There is more to this story than just this aminoacyl tRNA coming in and binding, as is shown on this slide. And so what I'll do is I'll come to this next slide, and then I'll come back to this slide. And so what happens here is there's actually an elongation factor called elongation factor TU, which is involved in this process. And what this EFTU does is, well, first of all, it's bound to GTP as well as it binds to the various aminoacyl tRNAs that will be involved in elongation. And this EFTU will help to deliver the aminoacyl tRNAs to the A site of the ribosome. And now this is where the role of the EFTU is important, especially important, because if the correct binding occurs between the anticodon of the tRNA and the codon of the mRNA, then that GTP gets hydrolyzed to GDP, and the EFTU is released, and that aminoacyl tRNA remains attached so that its anticodon is still bound to the codon of the mRNA, again, in the A site. And at that point, the elongation process would continue with what we'll talk about in just a second. However, if the binding is incorrect, so if that hydrogen bonding is incorrect, then what happens is the GTP does not get hydrolyzed. And very simply, the EFTU and the aminoacyl tRNA that it's bound to diffuses away. And then another one can come in and attempt to, correctly bind between the anticodon and the codon. So so the bottom line here for the EFTU is, again, it helps to deliver the aminoacyl tRNAs to the A site of the ribosome. And it also helps to ensure that we have correct binding between a tRNA and the codon of the mRNA. And again, if that is incorrect, then things just diffuse away and we try again. So now, for the sake of our discussion here, let's say, we went back to the previous slide. So for the sake of discussion here, let's say that this EFTU did indeed deliver an alanine to the A site, so an alanine aminoacyl tRNA to the A site of the ribosome, and we then had the correct binding between the tRNA and the codon of the mRNA. The next step here is that the amino acid from the P site gets transferred to the amino acid in the A site. Okay? This results in the formation of a peptide bond. Right? So now we have a peptide bond formed between our F-methionine and the alanine in this example. And obviously, if there is, if this peptide in the P site is much longer, well, what happens is the entire thing gets transferred to the A site here later on in elongation. But anyway, so now we have this situation here. And now if we go to 2 slides from here, and again, let me just walk you through this. Up here on the upper right part of this slide is where we left off on the previous slide. Okay, so this was all initially one figure, the slide that we were just looking at and this slide, but it would have been too small to scrunch it up onto one slide. So now this upper right part of the figure, again, is where we left off. Now, what happens is a process called translocation shifts the ribosome essentially one codon's length down the mRNA. So now compare this upper right figure to the upper left figure, right? So now the aminoacyl tRNA that had previously been in the P site is now in the E site. The aminoacyl tRNA that was in the A site is now found in the P site. And now the A site is open. It's, found with interacting with a new codon of the mRNA. And in this example here, it would be for leucine. And now what happens is essentially the next aminoacyl tRNA can be delivered. This would still involve the EFTU, as we just talked about. And so then this next one would come in and bind, and then in the next step, which is not shown here, the peptide that is found in the P site would be transferred to the amino acid in the A site. And this would occur over and over and over again during elongation. One thing that I need to expand upon for you here is that this event called translocation does involve an additional factor here. And this factor is elongation factor G, EFG. And EFG is involved in translocation. And so what happens now is after the amino acid from the P site has been transferred to the A site, what happens is this EFG, along with a molecule of GTP, can come in and bind. And what happens now is once it's bound, that GTP gets hydrolyzed, it gets converted to GDP, and when that happens, there's a large shift in change in that EFG. So there's a conformational change that occurs here, and it's this EFG that physically moves the ribosome along the mRNA. Okay, so again, it's this EFG that is involved here in carrying out this process called translocation. And now, this process occurs over and over again that we just talked about here with elongation until the ribosome encounters a stop codon. And there are no amino acids that are coded for by stop codons. There are actually no tRNAs that are involved here with stop codons, but rather there are a few release factors that are involved. And so now what happens is, again, our ribosome will be moving down the mRNA, and when it encounters one of the stop codons, what happens is either RF1, so release factor 1, or release factor 2, so these are both in the table here, these will bind to that site. So again, when the stop codon is found in the A site of the ribosome, either RF1 or RF2 will come in and bind to it. When this happens, when RF1 or RF2 is bound in the A site, this in turn will induce the cleaving of the newly synthesized protein from the ribosome. So now these RF1 and RF2 induce the release of the newly synthesized protein. And then after that takes place, the next release factor, RF3, comes in and causes RF1 and RF2 to dissociate. And then lastly, this ribosome release factor, this RRF, comes in and causes everything else to dissociate. So the large subunit comes apart from the small subunit. The mRNA is released. Any tRNAs that are still left there would be released as well. Okay, so now we've seen what happens with initiation, elongation, and termination. This next slide here, while it's complicated, is going to put everything together for us. Okay, this next slide is actually going to involve nothing that I have not talked about already. So, question?
So in this termination sequence, is it RF1 or RF2, or is it both?
Yeah, it's going to be RF1 or RF2 that is involved here. It doesn't need to be both. So either one would be sufficient. As you can see here, there's some overlap in the stop codons that they both bind to, but there's also a difference as well. So it's going to be one or the other that's involved here. So let me put this all together for you here. And again, there's nothing new on this slide here that we haven't talked about yet. So over here is, let me just orientate you. So over here is initiation. Over here on the bottom of the slide is elongation. And then over here in the upper right-hand part of the slide is going to be termination. And so if we go back to initiation, right, we see the IF1, IF3, and IF2 all playing a role in initiation. And again, at the end of initiation, we have our small and large ribosomal subunits that are found together. Notice here, it's omitting some details that we've had on previous slides, like the mRNA and the tRNAs, for instance. Well, after initiation, we have the EFTU delivering the amino-acyl tRNAs to the A site of the ribosome. After that occurs, we have translocation taking place that involves the EFG. And then from there, with elongation, we can come back over here and continue this over and over again until we encounter a stop codon, where we then proceed in this direction here, where either RF1 or RF2 will be involved. This would then be followed by the RF3 coming in and getting rid of the RF1 or RF2 that has done its thing already. Then the ribosome releasing factor comes in, dissociates everything else, and now the 50S, or the large ribosomal subunit, is freed from the small ribosomal subunit, and essentially we're back to where we began here. Okay, so that's what's happening here with translation. Are there questions with translation? Yes.
Is F-MET the only one that doesn't charge at A, it charges at P, right?
Yeah, so the FMET is going to start, oh, did I say A site? Sorry, the FMET is going to start at the P site. Yeah, that is the only one that will bind to the P site to start with. All the other amino-acyl tRNAs are going to enter into the A site. Yeah, so that's a good point to understand here. Okay, so again, during initiation, right, that first F-methionine tRNA comes into the P site, whereas all of the other amino-acyl tRNAs are going to be coming into the A site. Yes, that's a good point to reinforce here. Other questions? All right, well, I have a couple questions for you. So these will be review questions, and these are poll everywhere. So you get things ready. So here's the first question. What is the order of tRNA ribosomal binding sites through which a tRNA travels during the elongation stage of protein synthesis? Okay, let's see how we did. Very good. So it's going to go A, P, E. So that's the direction during elongation through which the aminoacyl tRNAs will move. And then the next question here is, which of the following is an elongation factor that is responsible for delivering the aminoacyl tRNAs to the ribosome? All right, let's see the answers here. All right, yeah, so the correct answer here is indeed the EFTU. Okay, so that's involved in delivering the aminoacyl tRNAs to the A site. EFG, what's EFG involved in? What process? Yeah, EFG is involved in translocation. IF1 is one of the initiation factors. What is this one here? The alphabet, very good. Just making sure you all were on board with that. So yeah, so EFTU is the correct answer here. All right, so let's move on to see what happens in eukaryotes. And as I mentioned before, some of the basics are going to be similar to what we've just been talking about with the prokaryotes. So for instance, the ribosomes here are going to have the A, the P, and the E sites. We're going to have mRNAs involved. We're going to have aminoacyl tRNAs involved. However, there are going to be some differences, and let me highlight a few of them for you here. So these are a few of the key differences. Actually, before we get to that slide, I'll highlight one first. So one of the key differences, I've been alluding to it all along here, right? Starts off with, what's the first amino acid going to be here in eukaryotes? Methionine, right? So the first AUG in eukaryotes is going to be regular plain old methionine. So there's no special tRNA for methionine here for initiation. Okay, so it's just going to be regular methionine that is used here. Another difference relates to how the translation start site is identified. And so what happens here is that the small ribosomal subunit, along with several initiation factors that aren't shown here, and we're not going to go into those here, but these bind to the 5' cap of the mRNA. And then this complex, once it's bound to the 5' cap of the mRNA, uses ATP as an energy source to essentially move this complex down the mRNA. And eventually, when it finds an AUG, and typically this AUG, it's not on the slide here, but typically there's going to be a sequence called a Kozak sequence that is typically near this AUG. And so when this complex here reaches this AUG with the Kozak sequence, what happens now is the initiation factors can be released and the large ribosomal subunit can come in and bind, and then elongation can take place. Okay, so that's one of the differences here between what we saw with prokaryotes and with eukaryotes. Some other differences here, at least during initiation, are highlighted on this slide, and this reinforces some of what I've said, actually most of what I've said previously, right? So with eukaryotes, we have that complex binding to the 5' cap, and then scanning for the AUG start site with the Kozak sequence. Whereas in the prokaryotes, we have the Shine-Delgarno sequence, and basically the small ribosomal subunit along with those initiation factors just simply bind to that site. The first amino acids we've talked about being methionine or formal methionine. We talked about the 3 initiation factors in prokaryotes. In eukaryotes, there are quite a few more. And then, of course, we talked about how the ribosomes differ from one another. So those are some key differences between translation in prokaryotes and eukaryotes. Are there questions on this? Yes?
So what exactly moves in eukaryotes that mRNA, or moves the unit, the subunit along?
Yeah, it's going to be some of those initiation factors that are involved in moving that complex along the mRNA. So some,
We don't need this specific.
right, exactly. We don't need the specific names and things of those. But yes, it is. That's a good question. It is indeed those, one of those initiation factors that is involved in the movement. Other questions? All right, just a couple of additional topics relating to protein synthesis, just to bring up here. The first is post-translational modifications. So after translation, there are a number of things that can happen to a protein, and more specifically, they're going to occur on certain amino acids of a protein. So for instance, when you're talking about histones, things such as acetylation, so an acetyl group or a methyl group can be added to some lysine amino acids of the histones. A very common one that occurs on proteins is phosphorylation. And phosphorylation can occur typically on serines, threonines, or tyrosines. So you should know the types of modifications and where they can take place. When we talk about signal transduction, a few classes from now, we're going to be talking about phosphorylation quite extensively. Hydroxylation can occur on some amino acids like proline and lysine. So you talked about that with collagen. Some formal groups can be added to some, for instance, to glycine post-translationally. And then there are some sugars as well as some lipids that can be attached to the proteins as well. And so, for instance, we can have glycosylation taking place as well as acylation or myristylation. For these last couple examples here, you're going to be seeing these later on because we haven't really talked about carbohydrates or lipids at this point. So for these bottom ones here, just know that that sugars and lipids may be attached to proteins as well. Another post-translational modification that can take place is also protein cleaving. And protein cleaving, the generic word for an enzyme that will cleave a protein is a protease. And so many times, or I should say there are many examples, especially in the digestive tract, where we produce a protein, and that protein is initially in its inactive form. But then that protein gets cut, so that way there, and once it's cut, it then becomes active. And you can see just a few examples here, right? So this large protein that gets produced, so perhaps an end of it gets removed, and then we end up with an active protein, or perhaps maybe the protein is cut into multiple sections, and perhaps multiple of these proteins are active. This is especially common, this example on the right, this is especially common for some viruses. Okay, so that's protein post-translational modifications. And then lastly, I wanted to just introduce you to some inhibitors of protein synthesis. And there are a number of these, as I've mentioned before. And you're going to encounter these again in the future, but just so you know, there are things such as streptomycin and aminoglycosides, tetracyclines, chloramphenicol, cyclohexamide, erythromycin, puromycin. These are all examples of protein synthesis inhibitors. Most of these are effective in prokaryotes. Nonetheless, cyclohexamide is involved in eukaryotes. Puromycin can have a role in eukaryotes as well. But nonetheless, mostly next year, when we get into pharmacology and we start talking about some antibiotics, especially some of these listed here, well, lo and behold, we're going to start talking about the ribosomes and especially the A site, the P site, and the E site of the ribosomes. And so it's helpful at this point in time for you to have a basic understanding of what's happening here with translation. All right, so that's where we will leave things off for today. Are there any questions? All right, thank you very much. If you do have questions, come on up and ask them. Otherwise, we'll see you on Wednesday. Have a great rest of the day. Thank you.